Hello Internet, welcome to my educational channel. Today we are going to look at the BTC calendar anomaly strategy. We are going to build and backtest it using Python as programming language and Google Colab as our coding environment. Before we start, the content is intended to be used and must be used for information and educational purpose only. Having said that, let's get started with coding. Started right away. So for our analysis, we have been using data from Crypto Data Download website, which is here. There are of course many different websites that you can use. I have also attached the link below if you need it. So you can go here on the website and you can just download any data source you're interested in. We are interested in the daily dataset, and so I have downloaded the daily dataset right here. Once you have downloaded, you come to the Google Colab, you click on the left icon here, you upload the data set, like you see here. I already did it, so I don't need to repeat that step. And then once you have it here, you can load the CSV data set into your pandas data frame. Okay, so our analysis again is about calendar anomalies, right? It's essentially a seasonal analysis, right? We will look at the BTC historical data set and create a day of the week analysis and run a backtester to simulate returns, right? First, we need to import our pandas library, import pandas SPD. Then we read the CSV data set and we skip rows, because if we don't skip the rows, what we have from the original data set, we have additional row that is not really important to us, and we don't have the namings here, right? So in order to avoid that, you just skip one row and then you have your data set. So next, as you can see, we don't have actually there is a datetime object. Oh, that's perfectly fine. So next thing is how would you convert? Let's say you don't have a datetime, you don't have a date object here. Takes the df Unix and then you say unit s and then you convert it into datetime object, and if you run it again, you see it's uploaded to date, right? Then what we need to do, we set our date column to index, right? So we set it, and the next thing is we just select the columns that we are interested in. So you have a list of columns. So in that case, we want to know the close prices, and then we take the volume and volume of BTC and volume of USD. It's not necessary for this analysis, but just for an example, right? How to do it. Then you have the data set. The next thing you need to sort your index, right? And then let's sort the index and display only the last 5 rows. You see the last date we have is the 2nd of December. So next thing is to plot the data set of the 3 columns that we have selected here. So to do that, you say df plot, you say subplots true. That means every time series, every column will be displayed in a separate window, and you define the size of your plot, right? So run it, wonderful. Okay, the way it is displayed like this is because I have set here to PLT style use 538. That's why it's still preset essentially. So the next thing is the day of the week strategy. Let's create a backtest, a simple seasonality strategy. We'll look at the historical time series data of Bitcoin to see if it has day of the week anomaly. The strategy aims to exploit the anomaly that the returns on a particular day are significantly higher compared to the other days, right? So let's define the algorithm. So first, let's calculate the percentage change for each day. Second, using the data for the last 60 days, like determine the day of the week on which the returns or the Sharpe ratio was the highest, right? For the next 2 weeks, buy the Bitcoin on that date, buy the previous day's close and sell at the close of the day, right? And then you repeat the step 2 and 3 for the entire backtesting period. So you have a window of 60 days. So the 60 days you use for training, finding the maximum Sharpe ratio. Then the next of the 60 days, the next 2 weeks, you use the train data and then you essentially you select the best performing day and you invest your money. And after the 2 weeks, you retrain again for the last 60 days, and you continue that step until you went through the whole data set. So the next step is to take our index dataset and to convert that into the day column into a day like this: Friday, Saturday, Sunday. So pandas provides a function. You just use on the index string for time to modulo A that will convert day into the day, as you see here. Okay, so next you just plot again just the close price and you label it. So you matplotlib as PLT, and then you set your style 538. You set the size of your plotting. Then you select from the data frame the close column and you plot, and then you label it and then you run. Okay, so now you have the time series plotted. So now let's compute the percentage change. So percentage change you can compute. So you select the column that you want to compute, the close, and then pandas provides a function that allows you to do that. So percentage change, and you assign that new series, resulted series, into new column data frame PCT, right? And then we plot that result. We say, okay, plot figure which configure the size. Then you take that column from the data frame df PCT and you plot, and then you label as daily percentage change and PLT show. You run it, you see it. So okay. So next, the day-Y Sharpe ratio. So first of all, what is a Sharpe ratio? Essentially, a Sharpe ratio is a measure the risk to reward of an investment. Right? SR, so calculated excess returns divided by volatility. Volatility is also known as standard deviation. So where excess returns, what are excess returns? So excess returns are investment return minus the risk-free return. The risk-free return essentially doesn't exist anymore, and it can be set as 0. So you take just the returns of your strategy divided by the standard deviation. So the Y-Sharpe ratio is computed in the below code. So you see the function that we use to compute our Sharpe ratio, right? So we use the group by function. So we say group by the day, and we are only interested in the PCT column. So we don't do yet the aggregation. The aggregation happens here. So we say we normalize it. So essentially we annualize the Sharpe ratio to the year. So that's why 252 business days times the day-wise returns, the mean value divided by the standard deviation, right? And then we have that function. So taking the entire data frame, which we just imported, and when we calculate the daily Sharpe ratio, we know, okay, so we see the daily Sharpe ratios by day, right? We see that historically looking, Monday is the best performing day, right? And Sunday is the worst performing day. So ideally at the end of Sunday, you would buy a Bitcoin and hold it for 1 day and then sell it. And historically you would have should have made some money. Let's look later on the performance analysis. So the Sharpe ratio day-wise is computed using the full data set here, as mentioned before. So generate signals. So let's generate the signals. The day-wise Sharpe ratio is computed for the past 60 days, as we described in our strategy. So second, for the next 2 weeks, 14 days, we buy the Bitcoin on the day with the higher Sharpe ratio, buy the previous day's close price and sell at today's close price. This is indicated by storing 1 in the signal column of the data frame df, and 0 indicated that we don't have any position in the Bitcoin. Okay, so looking on our data frame df, df.head, so that's our data frame. So we need to create another column that is signal column, right? We initialize it as npnen, which stands for not a number. Then we create and initialize a variable highest day that we will be using going forward. And then our window in this case is described like every 60 days, right? And then of df shape, if you run df shape, essentially you get a column that says you have, your data frame has 2,562 rows and 5 columns, right? 1, 2, 3, 4, 5, and in total 2,562 rows. So we will be iterating over each row, and every 14 days, you can say I modulo division 14 is 0. So if that is true, that means every 14 days, we recalculate our Sharpe ratio by taking I minus 61 and I minus 1. So we take a window of that period, and we calculate, so we slice the data frame into for 60 days, and then we calculate for that period the Sharpe ratio. And then Sharpe, so you get a PD series back, and if you apply IDX max of that series, you will get the day out. So for example, highest day could be Monday. So yes. So going forward for the next 14 days, you need to assign the signal where NP, where Monday essentially, if the day is Monday, you set it to 1, otherwise to 0. And you continue to iterate, and every 14 days you get essentially retrained, right? When you run that now signal generating process, and essentially then we look at the signals here, for example, in value counts, we can see, so on the total data frame, most of the time, Monday or Friday have been best performing days historically, right? Some days like Tuesday, Thursday, Wednesday, Sunday, they weren't very good, right? So just to give you a better insight what's happening here, because it's maybe a bit difficult for you to understand. So NP signal, NP NEN, if you run that, you get an NEN column. And for example, when we create the signal here, df log, essentially if you run df log, for example, df index of 5, in that case, for that data 5, and you select, so that is the position of the index, and that is which column you select, and what is the value of that position in that column. In that case was NEN, right? So if you say df day I log 5, that will become Wednesday, right? This is just an example here. So NP where df day I log 5 equals Wednesday, set it to 1, otherwise to 0, right? And then you get the result. In that case, it was 1. So next step is the final step is the strategy returns. The strategy returns are generated by multiplying the signal with the daily percentage change and stored in the strategy returns, right? So strategy returns becomes at the end a PD series, which is calculated df signal 1 or 0 multiplied by df percentage change, which we have historically calculated. And then we set our PLT figure of 18.5 and we label it strategy returns, and strategy returns cum sum, cumulative sum over that period, and then we plot it out, and that's our result. Okay, good. So now you have the results if you would run that strategy historically.